Okay, this is 5.1. I want to talk about how to solve problem A. It's not problem A, but part A. This part's not too bad. Part B, I want to go in a lot more detail because the solution manual does a really lousy job explaining where they came up with their values. The 2 pi just appears out of nowhere in the solution manual. I want to go over where that comes from. The equation for shear when there's torque is just going to be the torque that's being applied times C over J. Now J is just nothing but the polar moment inertia. So I write that down. So that's just polar moment of inertia. And these values, the J values, are going to vary. There's a different equation, whether it's a solid tube or has a hole through it. So for a solid shaft, the J value is just always going to be this. It's going to be pi over 2 times the radius to the 4th. And that's the polar moment inertia. And this R is from here to the outer radius. So if you're trying to find out what the shear stress is, say a different distance from the centroid or the center axis out to say here, you're not going to change this R value to match this. The only thing that would change here would be C here would become the P value. That's the distance out. But this equation we're always going to use. Now to find a max shear, you're just going to do the torque that is applied times the radius of the shaft over pi over 2 R to the 4th. Okay, now we can simplify this obviously because we have R4 here and an R here. So let's just start canceling things out. We'll cancel this out. We'll cancel this out. The 2 we can bring back to the top. That's going to give us a torque max of equal to 2T over pi. I meant to change that. I apologize. 3 pi times the radius to the 3rd power. Okay, so we can use that equation right there to find max torque. Sorry, not max torque, max shear. I always say that. If I say that in video, I'm talking about shear. Okay, now the problem wants us to determine the inner core using R prime of a shaft that resists 1/2 of the applied torque T2. Alright, so we're pretty much going to use almost the same equation, except we're not looking for T max right now. We can say that T, again I'm just going to put this as T, I'm going to use this equation right here, T times C over J. Now we know T here is T over 2. C value is going to be R prime. Okay, and we're treating this middle as just like a solid inner core. And then we're going to divide it by the polar inertia, so we're going to use the R prime as the radius. Okay, we need to simplify that. So when we simplify that, we can get rid of this part here. That's gone. We can make this a 3 and get rid of the 2's and the 2's. And then what we do when we simplify that, that's just going to give us, I'll do that in black. That's going to give us equals to the torque on the top over pi times R prime to the 3rd power. Alright, we'll circle that in blue. Alright, we also know that we can do a direct ratio using the T max. We know what the maximum shear is going to be. So if I want to find out what it's going to be at, say, R prime, here all I have to do is make a ratio of R prime over R multiply that times the maximum shear, and I can find out what the shear here is, because it's just a linear relationship. So I go back and I say the shear is going to equal to r prime, some radius, over the radius of the shaft times T max. However, we proved that T max is equal to this, so can't we not say that it's equal to r prime over r times 2 times t over pi r to the third power? And we'll simplify that. That's going to give me 2t r prime over pi times r to the fourth power. Okay, so I'm going to move some of this stuff down so we can finish this. Maybe scroll down a little bit more. Alright, so what you want to do now is you want to set these two equal for each other, because we're trying to find out. We're going to set this one and this one equal to each other because we're trying to find out what r prime is. And really, solution manual I think does a lousy job. So we take t over pi times r prime to the third power, set it equal to 2 times t times r prime over pi times r to the fourth. Alright, at this point, simplify what you can. Torque's gone, the torque's gone, the pi's gone, the pi's gone. Alright, we're looking to solve for r prime, so I'm going to bring r prime up here and bring everything else to the other side. When I do that, the other side, wouldn't the other side be r to the fourth over 2 is equal to r prime to the fourth. And then all we have to do is we're going to take this to the 1/4 power. So can we not say that r prime is equal to r to the fourth over 2 all to the 1/4 power? And when I do that, I get r over 2 to the 1/4 power. And that's where that's coming from. So that's r prime. Again, that is part A. Okay, the second part of this problem involves some integration, and the solution manual really, I think, does a lousy job. So got a lot to go over on this one. We said earlier that we can find the shear. Do it in black. We can find the shear by just taking the ratio of P over C. Again, all P is, again, is some distance away from the center, and C is the actual radius. And again, you don't have to use these symbols or these letters. You can use something. You can use C as R, whatever you want to do. Now, if we multiply that by max shear, this equation allows me to find the shear anywhere along here. All right. Now, we know that shear is nothing more than some force that's cutting across this area here. So can we not say, if we apply a force dF over dA, take some force across this small little area, then I get what's called the shear across that face. Now all we're going to do is rewrite this and say that the shear times dA, actually I'll put it over here, is equal to dF. Okay? Now we want to get this back into torque, and we know that torque is nothing more than some force times some perpendicular distance here. Okay, now here the distance is going to be P. So I'm going to multiply P by both sides here. That's going to give me dF times P is equal to the shear times P times dA. Alright, so now I have this equation here. Now, isn't this right here nothing more than we'll call it a delta torque? Because I got force times distance, I got some small torque. We'll set that equal to the shear times P dA. Okay, now we can integrate this. Okay, so we're going to set our integrals of dt. And we're going to go from 0 to t over 2, because it defined earlier. They want to know what the, right up here, when the torque is t over 2. And we're going to set that up to the integral. And here we're going to go between 0 and r prime of the shear stress times P times dA. Okay. Now we also earlier we said that T is going to be nothing more than the ratio between the P value, some distance. Let me show where that is. Some distance from the center axis over C times T max. Okay, so we're going to take this and put it back into here. Again, this is a pretty long integral. So we go 0 t over 2 dt of 0 r prime of P over C T max times P times dA. And then we can say T over 2, 0 of dt is going to be the integral of 0 to r prime of p squared. Write that p squared better. P squared over C T max times dA. Okay, the interesting thing here is you have to solve for dA. And the solution manual really does a lousy job of that, and just this dA, or this 2 pi appears. Show you what to do here. I'm going to paste in this cross section here. Oops. I'm going to drag it into here. And this all goes back to calculus 1 actually. So what we want to do is I want to find out what the area would be of all the way around this thing. And I'm going to let it be very, very thin, dp. Now we know the circumference of a circle is 2 pi r. So what I'm going to do here is I'm going to define this area here as 2 pi times p, because p is going to be the radius, and then I'm going to multiply it by dp. That right there is equal to the area of a small little slice of this circle if I went all the way around. Now what you do is you're going to take this and you're going to put it back in for dA. I should have made that dA right there. Alright, so now we'll rewrite our integral again. The integral of 0 to t over 2 of dt is equal to the integral of 0 r prime of p squared over c times t max times 2 pi times p times dp. Okay, now we're going to consolidate everything. And we can integrate this side anytime we want. It really doesn't matter. I can actually, we'll keep going. We'll leave it in there. 0 t over 2 dt is equal to the integral of 0 r prime. Actually, I'm going to erase that and bring out. Let's bring out everything that's not changing inside the integral. A couple things here. We know that 2 pi is not changing, and we know shear max is not changing. 0, and actually c is not changing either. We can bring it all out. Of r prime, p squared times p is p cubed dp. Okay, so when we integrate this, we will get t over 2, and then minus 0, so we can leave that out, is equal to 2 pi times t max over c. I should put my 0 in here, of r prime 0 of p to the 4th over 4. So then I'm going to have t over 2 is equal to 2 pi times my shear max over c times r prime over 4. Okay, we're almost got this problem done. And we'll write everything out. P to the 4th. Sorry, not P to the 4th. Or T over 2. I need to do. Sorry, I need to r to the 4th. I cleared up that. Just missed that here. It's r prime to the 4th power. R prime to the 4th power over 4. And we're almost there. There's only one other thing we need to do. Is that early on we defined t max as this. I'm going to grab this. Edit, copy that. I'll bring that all the way down. We'll drop that in. I'll grab that again. Edit, paste over here. Okay, we'll clean that up. And now we're going to take out t max and put this back in. And rewrite this thing one more time. T over 2 is equal to 2 pi times 2 times t over c times pi times r cubed times r prime to the 4th power over 4. Okay, now the last thing we know is the c value here. Look at here, the c value here is just the radius, so we'll take that back out. Rewrite it one more time, and we'll get t, make this like so I don't think it's part of this problem, t over 2 is equal to 2 pi times 2 times t times r prime to the 4th power over 4, and down below here I'll put the c and make the c an r times pi times r cubed. Alright, now we can really start simplifying. This is gone, 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 this is gone. So now we're trying to solve for r prime. So what I have here is 1 over 2 is equal to, oh, I need to cancel my t out too right here. My t went 2 because I canceled it out here. 1/2 is equal to r prime to the fourth over r to the fourth. So we bring r fourth to the other side, r to the fourth over 2 is equal to r prime to the fourth power. We take the 1/4 power of each side and we solve this problem as r prime is equal to r over 2 to the 1/4 power. So there it is. Quite a derivation, but it works. Best of luck.